Hello students, today we are going to discuss n type of p type of semiconductor. A p type semiconductor is an extrinsic semiconductor obtained by adding trivalent dopants with intrinsic semiconductors. The example of trivalent dopants are aluminium, boron, indium. Each of these has one electron less in outermost orbit of atom compared to 4 electrons in outermost orbit of silicon or germanium atom. So when a trivalent dopant is doped with pure semiconducting materials, a new semiconductor material is obtained in which the trivalent impurity provides one electron less. It contributes one electron less in the bonds formation between pure semiconductor atom and the trivalent atom. When trivalent impurities are added to pure silicon or germanium, a trivalent atom making covalent bonds with 4 silicon or germanium atoms contributes only 3 electrons. And we know whereas silicon or germanium provides 4 electrons, thus a vacant space of an electron known as hole is left there, which is available for conduction. The dopant trivalent atom is called because it has one electron less and it is required an electron for a complete bond formation between a single electron of trivalent atom and the 4 atoms of silicon or germanium. It is obvious that each dopant or trivalent atom provides one hole. So here the concentration of the electrons will be less compared to the concentration of the holes. Thus concentration of holes NH is very greater than concentration of, because the holes provided here are because of the trivalent dopant atoms and also due to the pure semiconducting atoms, whereas the electrons are being provided only due to the pure semiconducting material. So definitely the number of holes in the valence band will be more than the number of free electrons in the conduction band. That's why this type of impure semiconductor is known as p-type semiconductor. So this type of extrinsic semiconductor is known as p-type semiconductor. Now we will discuss energy band structure in an n-type and p-type semiconducting material. First we take case of n-type of semiconducting materials. At temperature greater than 0 Kelvin. The n-type semiconductor materials, they have the donor atoms which can provide the additional number of free electrons, and also the pure semiconducting material which can provide the equal number of holes and electrons. So the net concentration of the electron is much more than the concentration of the holes. So the energy gap, the forbidden energy gap between valence band and the conduction band is shifted towards the conduction band, and the large energy gap Eg is reduced to a smaller energy gap. Means now the lower temperature is required to maintain the conductivity of the semiconducting material or to increase the conductivity of the semiconducting material. If it would be a pure semiconducting material, we did require the energy gap Eg, a proper amount of energy to increase its conductivity. But when the impurities of donor atoms, when the impurities of pentavalent atoms is added in the pure semiconducting materials, the required energy gap is reduced to increase their conductivity. And since here the conductivity is due to the excess of the electron, those are the majority carriers in the n-type semiconducting materials, so it is known as n-type semiconductors. In p-type semiconductor, now in p-type semiconducting material, at the temperature greater than 0 Kelvin, with very small supply of energy, an electron from valence band can jump to the level Ea and ionize the acceptor negatively. The electrons rise up and holes fall down when they gain external energy. At room temperature, most of the acceptor atoms get ionized, leaving the holes in the valence band. Thus, at room temperature, holes in valence band have enormous amount comparative to the number of electrons. Means the hole concentration is much more than the electrons concentration. So here in p-type semiconductors, the majority charge carriers are holes. That's why it is known as p-type semiconducting material. That's all for today.